For my experiment, I wanted to see if a more porous crust, or a crust with more or larger holes, would change the explosiveness of an underwater eruption. I hypothesized that a less porous crust would have the effect of trapping the magma, thereby creating a more explosive eruption when the magma finally escaped the crust. To test this, I used wax to simulate the magma, and I used sand and small rocks to simulate crusts with different porosity. I put the wax in a glass, covered it with either sand or rocks, and then poured water over the top for the ocean. I turned the pan up to 250 degrees Fahrenheit and then waited. As a side note, I highly recommend using the properly treated glass beakers for this experiment, as I lost multiple glasses to the cause over the course of the project. While we wait for things to melt, let's talk submarine volcanoes. Currently, there are an estimated 1 million submarine volcanoes worldwide, with thousands of those still active. Most of the Earth's magma output in a year comes from these underwater volcanoes. Submarine volcanoes are underwater vents or fissures that magma erupts from, typically located at tectonic plate boundaries, and they are primarily basaltic. With divergent plate boundaries, the rate of plate movement is typically what determines the type of volcano that forms along the mid-oceanic ridge. The eruptions there are fueled by mantle convection and upwelling, causing eruption. With convergent plate boundaries, volcanoes form at subduction zones. These eruptions are fueled by volatiles added from subducting plates, which serves to lower the melting point of the magma to the point of eruption. With both of these, the weight of the water on top modifies their eruption style. Most submarine volcanoes are identified by their surrounding pillow basalts. If you watch closely, you'll notice that the wax cools almost immediately upon touching the cooler water. In the same way, when submarine volcanoes erupt, the crust surrounding the molten interior splits, lava slowly oozes out and flows for a short distance, and then quickly solidifies. Underwater volcanic eruptions that continue on long enough can form seamounts that eventually rise above the water and become volcanic island chains that we can observe today, such as the Hawaiian island arc. Ultimately, as you'll see by the end, I do not believe that there was enough evidence to support my hypothesis. While the eruptions do look slightly different, with the sand test erupting in more locations than the rock test, the eruptions still happen at a similar rate. To clearly state one way or another, we would need to run this test many more times. Potentially, something that may provide greater results would be to thicken the layers of sand and rocks. Thank you for watching.